A number you were told was settled may not be settled at all. For years, you were told the universe is 13.8 billion years old, clean, precise, case closed. But then James Webb looked deeper, found galaxies where they should barely exist, and forced astronomers to ask a question they did not want to ask in public. What if that number was never the final answer, only the best answer a certain model could give at the time? And by the end of this, you'll understand why some of the most careful scientists on Earth are no longer arguing about tiny details. They are arguing about whether the timeline itself may need to be rebuilt. To feel how strange this is, you have to start with what that number really means. 13.8 billion years is not a birthday stamped on the universe by some cosmic clock. No one was there with a stopwatch. It is an estimate, and a very impressive one, built from a model of how the universe expands, what it is made of, and how light from the early cosmos should look if that model is right. In 2013, and then again with fuller results in 2018, the Planck mission gave humanity the most detailed map ever made of the cosmic microwave background, the faint afterglow from a young universe about 380,000 years after the Big Bang. Scientists fed that map into the standard model of cosmology, called Lambda-CDM, and out came a number so precise it felt almost untouchable. About 13.8 billion years. To the public, it sounded like certainty. To cosmologists, it was always more conditional than that. It meant if the model is right, and if the ingredients are right, and if the universe really behaved this way all along, then this is the age you get. That still sounds strong until you remember what is inside that model. Most of the universe, according to Lambda-CDM, is not ordinary matter. Not stars, not dust, not planets, not you. Most of it is dark energy and dark matter, two things, and we infer from their effects, not things we can hold in our hands. Dark matter is the invisible extra gravity that seems to help galaxies and galaxy clusters hold together. Dark energy is the unknown cause of the universe's accelerating expansion. Together, they make up almost everything in the cosmic budget, while ordinary matter gets only a tiny slice. So, the age estimate that entered textbooks with such authority depends on a model whose biggest ingredients are still mysterious. That does not mean the model is useless, far from it. It has explained an enormous amount, but it does mean the famous number has always rested on assumptions that could, under pressure, begin to move. And pressure arrived from a direction nobody could ignore. Not from a wild internet theory, not from a shaky fringe paper, from some of the most advanced instruments ever built by our species. One of those was already causing trouble before James Webb even launched. This is the part most people never hear about when they are given the neat schoolbook version. There are two main ways to estimate how fast the universe is expanding right now, and they do not agree. That disagreement is called the Hubble tension, and the word tension almost sounds too gentle for what it really is. It is a standoff between two highly refined methods that should, if the full picture is correct, eventually converge on the same answer. Instead, they keep returning two different ones. One method starts from the early universe. That is the Planck route. It uses the ancient afterglow, applies the standard cosmology model, and predicts a present expansion rate of about 67.4 kilometers per second per megaparsec. The other method starts from the nearby universe, from stars and exploding stars, whose distances can be measured step by step in what astronomers call the cosmic distance ladder. First, you measure nearby stars by parallax, the same basic trick your two eyes use for depth. Then you use that to calibrate Cepheid variable stars, stars that pulse in a way that reveals their true brightness. Then you use Cepheids to calibrate type Ia supernovae, spectacular stellar explosions, bright enough to be seen across vast distances. That ladder, refined for years by the H0ES team led by Adam Rees, keeps landing near 73 kilometers per second per megaparsec. Not a little off, meaningfully off. Now imagine what that means. Two methods, two different eras of the universe, two sets of data gathered by very serious scientists who would love nothing more than to find a boring error and go home. But the error has not shown up. The gap has stayed. In fact, as the measurements improved, the disagreement became harder to dismiss as a fluke. That is one of the worst outcomes science can get. If uncertainty shrinks, but the answers still do not meet, then nature may be telling you the model is incomplete. For a long time, many astronomers hoped the local method had a hidden weakness. One target was the Cepheids themselves. Measure a pulsing star in a crowded galaxy with insufficient sharpness, and nearby starlight can blend into it, making it look brighter than it really is. That would distort the ladder and push the expansion rate too high. Then James Webb entered the story with infrared vision and sharper power in exactly the places that mattered. This was supposed to be a clean test. If crowding was fooling Hubble, Webb could expose it. But Webb did not rescue the neat story. It largely confirmed the Cepheid distances instead. In other words, one of the hoped-for escape routes began to close. The Hubble tension did not vanish. It got more serious. That alone would be enough to keep cosmologists awake. But then Webb did something even more uncomfortable. It looked back to the era when the first galaxies were supposed to be small, dim, messy, and just getting started. Instead, it found some that seemed brighter, more structured, and more evolved than many models had expected. The poster child for this shock became JD's GS Z14-0, a galaxy Webb confirmed at a redshift of 1432. In plain language, you're seeing it as it was roughly 290 million years after the Big Bang. That is not late. That is cosmic dawn, a universe still incredibly young. You expect early things there, primitive things. You do not expect to keep finding signs that some structures may have grown up with alarming speed. This is where the story becomes dangerous, because the public version often gets flattened into something too simple. You may hear that Webb broke cosmology. That is too strong. You may hear that nothing is wrong and it is all already resolved. That is too weak. The truth, and this is where science gets interesting, lives in the unsettled middle. Webb did not prove the universe is older overnight, but it did show that some galaxies in the young universe are forcing theorists to work much harder than they expected. And once you combine that with the Hubble tension, the old confidence begins to feel less comfortable. Think about what a galaxy really is, not just a patch of light. A galaxy is a city of stars, gas, dust, gravity, and time. To build one, you need matter to clump together, gas to cool, stars to form, stars to die, heavier elements to spread, black holes perhaps to grow, and structure to emerge from a universe that started almost smooth. All of that takes time. So when you see something surprisingly mature very early, you immediately ask the obvious question. Did it form much faster than we thought possible, or is the timeline we are using not as solid as we believed? And that question leads back to the opening hook, because this is not just about one weird galaxy. It is about a number that was taught as if it were final. The age of the universe is tightly tied to the expansion history of the universe. Change the expansion history and the age can shift. If dark energy behaves differently than assumed, the number can shift. If new particles existed in the early universe and changed how matter and radiation evolved, the number can shift. If gravity itself behaves differently on cosmic scales, the number can shift. The famous age is not a rock sitting outside the model. It is one of the model's outputs. That matters. Because another major project has also begun whispering that the story may not be as fixed as it looked. The dark energy spectroscopic instrument known as DESI has been mapping the large-scale structure of the universe using millions of galaxies and quasars. Its early results were not a declaration of revolution, and scientists were careful for good reason. But they hinted that dark energy may not act exactly like a perfect constant. If that hint grows stronger, then the name lambda in Lambda-CDM becomes a problem, because lambda is supposed to represent a cosmological constant, something unchanging. If the acceleration history of the universe has evolved in a more complex way, then the standard timeline may need adjustment. Notice the pattern here. No single result is enough on its own to throw out the age estimate. Good science does not work that way, but multiple pressure points are emerging at once. The expansion rate disagrees depending on how you measure it. Webb confirms local distance work more than some critics hoped. Webb also finds very early galaxies that seem surprisingly capable, surprisingly bright, sometimes surprisingly massive. DESI hints that dark energy may not be as simple as the old equation preferred. Each issue can still be argued around, but together they create a feeling that the universe may be telling us a deeper story than the one the clean public number suggests. And this is exactly where viewers often make a mistake. They assume uncertainty means science is failing. It does not. Uncertainty is how science looks right before it changes. Picture where we are standing. A species on a small, rocky planet around an ordinary star has built mirrors in space, detectors underground, surveys across continents, and mathematical tools sharp enough to test the age of everything. That is astonishing. But with each improvement, the universe answers with more detail, not always more comfort. You're watching the moment when better evidence stops fitting neatly inside old confidence. Now let's go deeper, because the early galaxies are not strange just because they are early. They are strange because of what early should mean. After the Big Bang, the universe was hot and dense. It expanded and cooled. At first, there were no stars, no galaxies, just a simpler cosmos mostly made of hydrogen and helium, with tiny density differences spread through space. Over time, gravity amplified those tiny differences. Matter fell into slightly denser regions. Gas collected. The first stars ignited. Their light began to end the cosmic dark ages. Later, galaxies assembled and merged and built the large structures we know. That is the broad picture. It works. But the details matter. How fast can those first structures really form? How quickly can gas become stars? How rapidly can black holes grow? How much dust and heavier elements can appear in a short span? Webb has made those questions much harder to keep abstract. When astronomers expected a handful of faint smudges and instead began seeing populations of unexpectedly luminous objects, the tone of the conversation changed. One especially curious class became known as little red dots, compact sources in the early universe that are still being debated. Are they galaxies packed with stars? Are they black holes feeding behind veils of dust? Are they some mix of both? The point is not that astronomers have no ideas. The point is that Webb keeps finding objects that demand explanation faster than consensus can settle. This is the moment I want you to pause and think like a detective, not a fan. When different clues start pointing to the same unease, you do not need to declare the case solved, but you do need to stop pretending there is no case. If you think this is just a harmless calibration issue, or if you think it means the whole Big Bang is dead, put your theory in the comments as one word: timeline. I read those, and in a story like this, your first instinct says a lot about how you see science itself. Because there is a temptation to oversell, let's be brutally honest. The Big Bang model has not collapsed. The cosmic microwave background is still real. The universe is still expanding. Primordial element abundances still matter. Galaxy evolution is still a real field full of success, not smoke. The problem is subtler and more important than clickbait gives it credit for. The question is whether the standard version, the one that became neat enough for textbooks, is complete enough to survive the precision era. That is a much more serious issue than shouting that everything was wrong. The danger is not that all of cosmology was fake. The danger is that a simplified, stable story became culturally frozen just as the data began to turn unstable. And that has happened before. Human beings have a habit of promoting the best current map into a final map. For a while, astronomers thought the Milky Way might be most of the universe. Then it became one galaxy among countless others. For a while, many thought the universe might be static. Then it was expanding. For a while, its age estimates wandered wildly, sometimes much older, sometimes much younger, depending on the data and methods available. The history of cosmology is not a straight march toward one perfect number. It is a sequence of revisions driven by better instruments. That does not weaken science. It is what gives science its power. But it should make you cautious anytime a frontier estimate gets sold to the public as permanent. There's another clue hidden in the way astronomers talk among themselves. In papers, they often use phrases like tension with predictions, challenge to standard assumptions, unexpected for current models, difficult to reconcile, potential new physics. To the public, those phrases can sound mild. Inside science, they are often loaded. Researchers are trained to be careful, not theatrical. So when the language starts sounding uncomfortable across multiple papers, you should pay attention. Especially when the discomfort comes from data everyone agrees is worth taking seriously. Now imagine the universe as a clock, but not a simple one. Not a neat wall clock with one gear. More like a vast machine whose hands depend on hidden parts. If you misjudge one gear ratio, the displayed time changes. That is what the age estimate is like. Change the expansion history and the clock changes. Change the amount or behavior of dark energy and the clock changes. Add early dark energy, a proposed temporary extra energy component in the young universe, and the clock changes. Modify the properties of dark matter and structure formation shifts. Adjust neutrino physics and the timeline shifts. These are not cosmetic edits. They reach into the machinery that turns observations into age. This is why the age of the universe and the Hubble tension are not separate stories. They are tied together. A higher present expansion rate, all else equal, generally points toward a younger universe. But once you allow the full model to change, the situation gets more complicated. New physics in the early universe could alter how we infer both the expansion rate and the age. A changing dark energy component could reshape the cosmic expansion history in ways that move the number. That is why you see researchers proposing multiple pathways rather than one clean fix. The universe is not offering a tidy answer. It is forcing cosmology to test several. One of the more publicized responses came from researchers exploring whether the universe could be older than the standard estimate, sometimes significantly older, if alternative assumptions are used. These papers attract headlines for obvious reasons. But here again, caution matters. A provocative new age is not automatically the new truth. Many such proposals are speculative, incomplete, or strongly debated. Their importance is not that they have already won. Their importance is that they exist at all in a field that, on the surface, looked settled. The very fact that serious people are trying models where the number moves tells you the old confidence has cracked. But Webb's challenge is not only about age, it is about pace. How quickly the cosmos did what it did. Suppose the universe really is very close to 13.8 billion years old. Then some early galaxies may have formed stars and assembled structure faster than expected. That would mean astrophysics inside the timeline needs revision. Now suppose the expansion history itself is off, and the universe turns out older or differently timed in key eras. Then some of those galaxies may look less impossible because they had more room, or because the background conditions were different. In one path, the timeline survives, and the formation models change. In the other, both the timeline and the formation models may need surgery. But that was not the strangest part. Not even close. Because some of the strangest pressure does not come from galaxies at all. It comes from what the standard model assumes exists in order to make everything fit. Dark matter remains undetected in laboratories, despite decades of increasingly sensitive experiments. That does not mean it is not real. It may be real in a form we have not yet found. But the silence matters. Meanwhile, dark energy, the biggest piece of the cosmic budget, is not something we understand in a direct physical way. We know the expansion of the universe is accelerating from observations of distant supernovae and other probes, but why it accelerates remains one of the deepest open questions in physics. If your cosmic age estimate depends on a universe dominated by components whose nature is still unresolved, then precision should come with humility. And humility is exactly what the best scientists usually show, even when headlines do not. They know a model can be powerful and incomplete at the same time. Newton's gravity worked brilliantly for centuries, and still works for countless practical things. Yet Einstein gave a deeper picture. In the same way, Lambda-CDM may remain broadly right while still needing important changes, or it may turn out to be a temporary bridge towards something richer. Either way, the public often hears certainty long after the experts have moved on to caution. Take the oldest stars. Years ago, one famous star, HD 140283, nicknamed the Methuselah star, seemed so old that early estimates made it look awkwardly close to, or even older than, the universe itself. Later refinements reduced that tension. Today, it is not a clean contradiction, but its history is revealing. It shows how sensitive age estimates can be and how quickly apparently settled numbers can become uncomfortable when measurements improve. The same is true for ancient globular clusters, dense swarms of very old stars around galaxies like our own. They do not prove the universe is older than standard cosmology says, but they remind us that cosmic chronology is a delicate business. You're not measuring the universe with a ruler, you are reconstructing it from clues. Now let's return to JD's GS Z14-0, because this galaxy matters for more than its headline. Seeing a galaxy from roughly 290 million years after the Big Bang is already remarkable. But later observations also suggested it may be more chemically mature than many had expected for such an early time. In astronomy, when people say a galaxy is chemically enriched, they mean it contains heavier elements produced inside stars. In other words, stars had to live and die to make those elements. That points to rapid early star formation and fast evolution. Again, not impossible by decree, but uncomfortable enough to force models to stretch. The young universe is starting to look less like a simple nursery and more like a place that got busy very fast. Try to picture the scale of what that means. Light from such an object began its journey when the universe was only a tiny fraction of its current age. That light crossed expanding space for more than 13 billion years before hitting a mirror built by primates who learned to split atoms, write equations, and unfold gold-coated instruments a million miles from Earth. And when that ancient light arrived, it did not merely tell us something old. It told us our confidence might have been too young. This is why the room goes quiet in science. Not because people love drama, but because the data does not care what they hoped would happen. A quiet room in astronomy can be louder than a press conference. It means the implications are being calculated in real time. If the telescope is right, then something downstream has to bend. Maybe the star formation recipes need to change. Maybe black holes grew faster than expected. Maybe dust formed faster. Maybe feedback physics in young galaxies is different. Maybe dark matter halos assembled structure earlier. Or maybe, and this is the thought hiding behind the whole title of this story, the universe is not being timed quite the way we thought. There is a part of this story many people miss because they are waiting for a single dramatic announcement. Science often changes before the public notices it has changed, not with one trumpet blast, but with an accumulation of careful papers, conference talks, revised uncertainties, and increasingly awkward language. By the time a textbook sentence gets rewritten, the frontier may have been wrestling with the problem for years. That means you may already be living in the gap between what schools still teach cleanly and what working researchers discuss more nervously. There is another part of this story. NASA and the big observatories will keep refining in the years ahead, and that future evidence may matter even more than the first shock. So stay with this one first, because the next few years are likely to decide whether this becomes a tweak or a rewrite. So, what are the main possibilities? Let's lay them out without pretending we know which one wins. First, the standard age could remain roughly correct, and Webb's surprising early galaxies could be explained by better astrophysics. Maybe stars formed in bursts more efficiently than expected. Maybe black holes lit up young systems in ways that made them seem more mature. Maybe some mass estimates were initially too high and later get revised downward, as has already happened in some cases. That is the conservative path. No revolution in age, but a big update in how early structure forms. Second, the Hubble tension could be pointing to new early universe physics. Something about the young cosmos before or around the time of the microwave background may differ from the standard model. That could change inferred cosmological parameters and perhaps shift the age estimate. Many proposed solutions live here, including early dark energy models. These are not proven. Some help with one problem and create another, but they are serious attempts to preserve as much as possible while fixing what hurts. Third, dark energy itself may be more dynamic than a simple constant. If Desi's hints grow stronger, the cosmic expansion history may need a more flexible description. That would ripple through age estimates and through our picture of how the universe evolved over time. Again, not confirmed, but no longer a crazy question. Fourth, the deepest possibility is that the standard framework is missing something broad, perhaps in gravity, perhaps in the dark sector, perhaps in how matter clumps on large scales. This is the most radical path, and the one scientists are most cautious about for obvious reasons. You do not abandon a successful model lightly, but it remains on the table because the stubbornness of the anomalies keeps it there. And this brings us back to you, because it is easy to hear a story like this and feel either thrilled or cheated. Thrilled because the cosmos is more mysterious than advertised. Cheated because you were told the number was settled. I think the better response is something more mature. You were given the best simplified answer at the time, but simplification is not the same as permanence. When science reaches classrooms, it often arrives after being cleaned up. All the arguments, the uncertainty, the active repairs get trimmed away. That is good for teaching basics. It is bad for showing how knowledge really works at the frontier. Knowledge at the frontier is alive. It breathes. It contradicts itself before it resolves itself. It produces tension before clarity. That is what you are seeing here. And it matters because the age of the universe is not trivia. It connects to everything. How long stars had to forge the elements in your blood. How quickly galaxies assembled. When black holes appeared. How the Milky Way's history fits into the wider cosmic story. If the timeline shifts, even modestly, many chapters must be reread. And yet the most honest ending is not a verdict. It is a recognition of where we stand. Right now, the safe claim is not that the universe is definitely older than 13.8 billion years. The safe claim is that the confidence surrounding that number is being stress-tested by some of the best data humanity has ever collected. The number may survive with adjustments. It may move. The model may bend and hold, or it may need more serious reconstruction. The reason this matters is not that science failed to give a final answer. The reason it matters is that science is still brave enough to let reality overrule comfort. So if you were taught that the age of the universe was settled forever, that was too simple. If you're now tempted to believe one telescope destroyed everything overnight, that is too simple too. The truth is more unsettling and, honestly, more beautiful. We built a machine to look farther back than ever before, and instead of handing us closure, it handed us a deeper puzzle. A universe once presented as time to the decimal may be more flexible, stranger, and less finished in our understanding than we thought. Somewhere in the next few years, more Webb observations, more DESI data, and more work on the Hubble tension may force the field toward a clearer answer. Until then, the most truthful thing you can say is that 13.8 billion years is still the standard estimate, but no longer the untouchable one. And maybe that is the real mystery hidden inside this whole story. Not whether a textbook number changes, but whether you are willing to watch knowledge change while it is still happening. Because out there, beyond the Milky Way, beyond the first ordinary stars, beyond the faintest red-shifted light,